folks, let's talk about bond enthalpy and potential energy diagrams. We need to address a big question. What's actually causing these changes in chemical energy during a reaction process? Well, it turns out there's really two answers: breaking bonds and attractions and making bonds and attractions. When we break a bond, we are overcoming the attractions between the electrons involved in the bond and the nuclei in a covalent bond, or between the cations and anions in an ionic bond, or between a metal and the electron Z in a metallic bond. We are separating particles that were attracted from one another. This is hard. It takes energy. Breaking bonds always requires energy. It is an endothermic process. The converse is going to be true for making bonds. If you are making bonds, you are bringing two particles and you're allowing them to form a new attraction. This is a stabilizing process and it releases energy. Making bonds is always an exothermic process. I'm going to say it again because it's really important. Breaking a bond always requires energy. You put energy in to break a bond. Making a bond releases energy. You get energy out when you make new chemical bonds. Okay, so let's talk about how this connects to the LOL diagrams we already drew, and let's take this to the next level, what chemists actually use in real life, which are potential energy diagrams. They are going to be added to convey more and more information in a way that LOL diagrams cannot accommodate. So, you saw this in our previous video, the reaction between barium nitrate and sodium sulfate in a double replacement process to form barium sulfate and sodium nitrate. Delta H for this reaction is a negative 67 kilojoules per mole reaction. So as this reaction occurs, every time this happens for 1 mole of material, as written, you end up giving off 67 kilojoules of heat. We saw the LOL diagram before. We saw that energy leaving for your exothermic process. So you're seeing that it's exothermic both in the picture and in the fact that delta H is negative for an exothermic process. Now, potential energy diagram wise, what a potential energy diagram does is it takes kind of this bar diagram and it makes it not a bar diagram anymore, not a bar chart anymore. You have on your x-axis the reaction progress, which means on the left side of this graph, you're going to have your reactants, the energy of those reactants, and on the right side, you're going to have your products. And then the y-axis is potential energy. This is chemical energy, phase energy, all the different things associated with the potential energy of your reactants and of your products. What we're going to do is we're going to start by just drawing an arbitrary energy position for our reactants, kind of like we just picked a number of blocks for the LOL diagram. I'm just going to pick a place to draw my, my starting point for my potential energy diagram. And I know delta H is negative. So over where my products are, I need to subtract the amount of energy that I have in my system. So I'm going to draw a line that is lower on that graph. And this means during the process, my energy goes from where the reactants are down to where the products are. That's baseline. We're going to add more in just a minute, but that's the baseline process for drawing these potential energy diagrams. So they are very similar to an LOL diagram, and they show you where you start and where you end. Let's look at one more, and then we'll add stuff to it. Here's our water decomposing again. So we've got water breaking down into hydrogen gas and oxygen gas. Delta H for this reaction, the change in the energy, the change in the heat for this reaction is a positive 572 kilojoules per mole. You see it in the LOL chart. You see the fact that this is an endothermic process because I'm adding energy. It's going into my system. When I do this as part of a potential energy diagram, again, arbitrary starting point, put your reactants down there. My products need to have more energy, so I'm going to add energy, so they're going to have a greater potential energy. I'm going to put them up there. So in the absolute baseline piece, I've gone from reactants with low energy to products with high energy. That is your endothermic process. Okay, to add to it, we need to have a concept called bond enthalpy. What bond enthalpy is the energy it takes to break a bond. Or, if you're forming bonds, it's just the opposite of that value. And these are numbers that we can work with. Let's take a look at two examples here. So if I have HCl and I break it apart, so I'm starting with hydrogen and chloride together, hydrogen and chlorine together, and I break the molecule, I break that bond. I get a hydrogen atom and a chlorine atom. That process, delta H, is a positive 432 kilojoules per mole. We are breaking a bond. Breaking a bond is always endothermic. You always takes energy to break the bond. You can do the same thing for HBr, break the hydrogen-bromine bond. If you look at these values for your enthalpy, for your bond enthalpies, you will see that delta H for the HCl process is larger, which means that this is a stronger bond because it was harder to separate HCl than it was to separate H and Br. So that's one piece of information we can pull out of bond enthalpies. If we go to form a bond, I've flipped the process around. So let's say I do the opposite. I take H and Cl and I form HCl. I have now exactly reversed the process. My value for delta H will be a negative 432 kilojoules per mole for this reversed process. So a bond enthalpy, the numbers that are tabulated that you'll be working with, those are always for breaking the bonds, but I can just reverse the sign if I want to make it for making a bond. Well, how is this going to add to my potential energy diagram? Let's go take a look. We can use these bond enthalpies to actually predict values for how much delta H is going to change and kind of put numbers to those graphs that we were just making a second ago. So, for example, if I have H2 and F2 and it's going to make 2HF. Let's start with an arbitrary base point. These are my reactants. So this is hydrogen and fluorine as a gas. Those are the reactants that I'm starting with. We need to figure out whether this is going to be endothermic or exothermic. And so we're going to use our bond enthalpies to estimate the energy change associated with this. So in order to make the products, I have to rearrange the atoms. So I have to break all the bonds in the reactants, and then I'll form new form new bonds in the products. Well, H2 is hydrogen bonded to hydrogen, and F2 is fluorine bonded to fluorine, and then HF is, well, hydrogen bonded to fluorine. To break the HH bond takes 591 kilojoules, and since there's just one of them, takes 591 kilojoules. That's what it says in my table. To break the FF bond, that's the next one down here, it takes 155 kilojoules. So to break both of those, I just add them together. 646 kilojoules to break those bonds. And then I'm going to make bonds on the other side. I'm going to make 2 HF bonds, and each HF bond comes in at 567 kilojoules. And this is 1,134 kilojoules that's going to be given off when the new bonds form. So when I go back to my potential energy diagram, I'm going to draw an arrow showing that I'm going to break the bonds, and it's going to require 646 kilojoules of energy to do so. And then I'm going to make new bonds. This is so not to scale. I'm going to make new bonds, and that releases 1,134 kilojoules of energy. I am releasing more energy than I put in, so I can tell that this is an exothermic process, and I can actually calculate a value for delta H for this reaction. I put in 646 kilojoules of heat. I release, so it becomes negative 1,134 kilojoules of energy, and so this is a negative 488 kilojoules. And so I can come back to my graph here and I can tell you that this change corresponds to a negative 488 kilojoules of energy because I put in 646 and I got out 1134. We are almost done. Let's take a look at one more problem where we're doing this estimation and adding that information to our potential energy diagram. Okay, so we have C2H6O. This is ethanol as the common name for this molecule, so it's an alcohol. We're going to burn it, so we're going to react it with oxygen and make carbon dioxide and water. When you have a problem like this, it's really important that you draw out the molecules so you can figure out what the bonds are. So the first thing I'm going to do is take my ethanol and I'm going to draw it out. Remember, we talked about this earlier this year, that carbons and oxygens will form a central chain. And then the hydrogens will be added on after the fact, such that every carbon forms 4 bonds and every oxygen forms 2. And then I have 3 oxygen molecules, and if you remember from our Lewis dot structure fun, oxygen forms a double bond when it is O2. And this is going to react to form carbon dioxide, which is more double bonds to oxygen, but this time it goes to the carbon. And then water, which you guys know is oxygen in the middle, and a single bond to each of those hydrogens. Okay, so there's what I'm breaking apart and making anew. Time to add up all the pieces. This gets to be a little bit of adding. Okay, in my left-hand molecule, I have 1, 2, 3, 4, 5 bonds between carbon and hydrogen. So I've got 5 CH bonds. Each of those come in at 591 kilojoules. To make it fit, I'm going to drop the kilojoule bit. I will add that because I also have to break the CC bond, and that comes in at 348 kilojoules per mole. There's 1 mole of bonds. I have a CO, that's at 358, and I have an OH, so I've used that one, this one, at 463. So that's all the stuff to break apart the ethanol. Now I need to break apart my 3 oxygens. So I've got 3 O2s, each at 495 kilojoules. Okay, so there's all of my reactants. This sums up to 4,719 kilojoules. That's how much energy I have to put in to break that apart. That way it can form something new. On the other side, I am going to get 4 C double bond O forming when I do this. And so that's 4 times 799. And I will get 6 OH bonds forming. And OH comes in at 463 kilojoules per mole. And so when I add this up, this is 5,974 kilojoules. I get more energy out than I put in this case. So when we go to our little diagram over here, arbitrary starting point. These are our reactants. I'm just going to write reactants right now. You could totally not label it, knowing that that is what is on the left, or you can label it with your reactants. I'm going to put in 4,719 kilojoules to break apart my molecules into component atoms, and then from that point I'm going to get out 5,974 kilojoules of energy. And so my overall change in reaction, going from reactants to products here, this corresponds to delta H. Delta H for this reaction is going to be the positive 4,719 kilojoules minus that 5,974 kilojoules that I get out because I'm making those bonds. This is negative 1,255 kilojoules per mole as the reaction is written. So for every 1 mole of alcohol reacting with 3 moles of oxygen and producing 2 moles of CO2 and 3 moles of H2O. We are going to keep adding to these potential energy diagrams as the year goes on, but they are a great starting point for summarizing how the energy is changing and what's going on, so use them well.